Now, let us look at this, the Bohr shift, okay? A slightly, what we call this, adjustment to our extractions of the O2 from hemoglobin. We want hemoglobin to release more O2, even more readily in this case, okay? So from previous graph, for previous oxygen dissociation graph, we look at it, we look at the O2 saturations depend on the partial pressure O2, correct or not? Okay, because when you plot the graph, this is percentage saturation versus partial pressure O2. And then you get the graph in sigmoid shape. Correct. So it means that now we know that percentage saturation actually depended on partial pressure of O2. Correct. That's why when we increase the partial pressure O2, we get the percentage saturation increases. If not, it will be a flat straight line, correct? Okay, but it's not true if you look at it only, if you say that only depend, okay, only depends on partial pressure O2. In fact, partial pressure of CO2 has effect on hemoglobin dissociation curve. So let us look at this. So this effect is known as a Bohr effect. So what's the Bohr effect? Bohr effect actually states that, okay, the influence of the CO2 on the sigmoid shape of the hemoglobin dissociation curve make this dissociation curve now shifted to the right. So write down, low CO2 concentration means normal. Are you clear? Normal, not vigorous activity. Yeah? Not vigorous activity. It's just a normal activity. High CO2 concentrations basically means that when we have mild to vigorous activity, where we have high rate of aerobic respiration. When we have high rate of respirations, then we release more CO2. So therefore, partial pressure of CO2 is high. So we are going to look at this, how partial pressure of CO2 actually affect, okay, the positions of the dissociation curve now. Okay, So let us look at this Bohr effect. What Bohr effect actually, or Bohr shift actually take place? So if you look at this, this is a percentage saturation. Okay, this is a partial pressure of O2. Okay, and then we are going to have this, the graph. Sorry, I draw it again, not so sigmoid, make it more sigmoid. Okay, so again, we don't study all the part. We only study at 10 kilopascal. So here we have about 95% saturation is at the sea level. Okay, and then we look at here, 2 kilopascal. Okay, we go up and we study here. So what is the value? Roughly about 20%. Okay, so 20 and 95. So why we choose 2, we choose 10? Because partial pressure O2 in the lung is equivalent to about 10 kilopascal, because the fresh air that we breathe it in contain high concentration of O2. How about respiratory tissues? In the respiratory tissues, we do know that the oxygen's concentration is low because respiratory tissues or active tissues continually use up the oxygen. So partial pressure O2 is low. Okay, this is under normal conditions. But when the tissues having high activity, where they're going to release high volume of CO2. Therefore, partial pressure of CO2 increase. Are you clear? Then you can see that this graph, this graph will shift to the right. Use orange color. Okay, so can you see that it's shifted? The graph actually shifted to the right. Okay, so when it shifted to the right, what actually indicates here? If shifted to the right, read it here now, guys. Do you realize that at 2 kilopascal, at the muscle tissues or liver, they carry out active metabolic reactions, or they have the high respiration rate? Then you can see that now become roughly about 10%. When the graph shifted, okay, so when the curve shifts to the right, indicate what? It decreased affinity. When decreased affinity means more O2 is released. Okay, more O2 is released. And it makes sense, correct or not? Right? Does it make sense? Yes, because when the tissues carry out higher activity, they release a lot of CO2, means that they are having higher rate of aerobic respiration. And with a high rate of respirations means that they demand more O2. So this is how we can actually ask the hemoglobins to release more O2. Can you see that? So in this graph, this is a normal. This part is a normal partial pressure of CO2. This one is increased partial pressure of CO2. So it means that when the cells release more CO2, automatically we're going to extract more O2 from the hemoglobin. So making the saturations now drop to 10%. Are you clear? Drop to 10%. So if you look at this, what's the idea of 20%? As I said yesterday, talk about this. The idea of 20% of the saturation means that majority HbO2, which is 25% saturation, and some Hb, which is 0%. So therefore, you get a mean around 20% saturation. Cannot. But now you drop to 10% saturation. So what is ideal 10% saturation? The ideal 10% saturation means that, okay, almost 50% of the hemoglobin, they are HbO2, and another about 50% of the hemoglobins Hb. Can you see that roughly? Okay, about 50%. So therefore, you get the average because this is 25%. Okay, this is 0%. Okay, can I see that? So more than 50%. So in this case, you get a mean roughly about 10% saturation. So if you compare these two, I'm going to highlight it. You can see the effect. This one, you have majority HbO2. But now, decrease to about 50% HbO2. Means that we release even more O2 for the respiring tissues to carry out aerobic respirations. Now, in the context of CO2, always remember, in the context of CO2, when release CO2, okay, sorry. When you say that release CO2, always be careful. CO2 only can be released by aerobic respiration in mammal. Are you clear? Anaerobic respiration in mammal won't release CO2. Are you clear? Okay, so always remember. So let me stop a while. So students always now have confused about this, the Bohr effect. Okay, in the Bohr effect. Why? Because if you look at the graph here again, percentage saturation versus PO2. Okay, PO2. Okay, so you have this graph, sigmoid curve. You need to learn how to draw, yeah, guys. So this is under normal partial pressure. Oh, sorry. Let me use a different. Okay, so we read it 10 kilopascal. Okay, so 95%. Okay, and then we have these transparent tissues, 2 kilopascal, about 20%. Correct. Okay, so this is under normal PCO2. Okay, under normal PCO2. Now, if Bohr shift saying that it's shifted to the right, right? Shifted to the right. So affinity also decrease. So if at 10 here, if you read maybe 90%. Can you see that? Yeah, here can give me about 10%. But the thing here is always remember, if you analyze the graph, you cannot simply, just look at the particular graph only. This is a PCO2 high. Okay, now look at this. 2 kilopascal here represent the lung. What was that? My mistake, sorry. Muscle, for example. So let's say you carry out the running process. So when running process, let's say you run, means that your partial pressure of CO2 will be high. So which part of the graph you read? You're going to read at this graph, guys. We're going to read it here. Why? Because when you run, you carry out activity, your CO2 concentration is high. So therefore, I read this 10%. Okay, but in the lung, even though you run, no effect, because the lung won't contract. The lung won't run together. It won't actually pumping hard. Can you see that? And in fact, when running, you increase the breathing rate. You bring in more oxygen in. So which part of the graph you have to read? You have to read it here, because in the lung, there's no effect. So the partial pressure of CO2 actually is low or normal, because we release the CO2. So which part of the graph we read? We read it here. So means that it still remain at 95%. So from 95 to 10%. So actually decrease more, release more. It's not 90 to 10, but it's 95 to 10. Okay, always remember this one, we read it for the lung, because lung always have high partial pressure O2, low partial pressure of CO2. Are you clear? How about muscle? Muscle then depend. If under normal, at rest, something at rest, in this case, okay, then our partial pressure of O2 is low, but partial pressure of CO2 normal. But if you run or have an activity or mild to vigorous, okay, exercise, then partial pressure of O2 is low, partial pressure of CO2 now increase. And because of increase of partial pressure of CO2, then we do have the Bohr effects, or Bohr shift the graph to the right. Okay, you can take diagrams here. So which part of the graph you need to actually focus? So we say that the Bohr effect is the influence of CO2 on the sigmoid shape of the hemoglobin dissociation curve, highlight shifted to the right. Okay, when shifted to the right means decrease affinity. Okay, decreases the affinity. So hemoglobin now become less saturated. at high partial pressure of CO2. Okay, compared to the normal condition. Okay, now I also want you guys to put into this diagram. We haven't learned about this yet, okay, for tomorrow or the next lessons. So look at this. Low CO2 concentration, sometimes we say pH is low. I said pH is high. High pH. This one, high CO2 concentration, pH is low. We're going to learn about this tomorrow. Why? Okay, so sometimes question label it differently. They label pH normal or high pH, low pH. Okay, so you can see that now the graph shifted to the right. If you use, I mean, at the, okay, at 2 kilopascal, you can see that roughly about 20% for normal, but lower, okay, for the high CO2 concentration or high partial pressure of CO2. Okay, so with this, I've done for today's lesson.